Hey everyone, we are continuing with differential equations, and this time we're looking at them the way they usually show up, which is in context, aka story problems, genuine, fake, real-life examples. So say you have a population of 1,000 people in some small town, and the population is currently growing 5% a year. Write a differential equation that expresses this fact. Okay, you're probably looking at that going, how is that a differential equation? I know that's that dy dx equals blah, 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 whatever. And you're kind of going, huh? And that's okay. Okay, another way you could consider this is like that the population's growing 5% a year. You could consider it something more like this. The rate of change of population is 5% of the population. I know that's like a big leap to get from the sentences that are typed to this guy. But if you think it through, it is what it's saying, because this will help us to get a differential equation. So rate of change of population, rate of change, when you see rate of change of something, that's going to be a d something dt. In this case, population, so how about dp dt? So, and then is 5% of the population. So if it's growing 5% a year, it's 5% of the population, and if p is the population, then it's 0.05 times p, so 5% of the original p. So here's our differential equation. So now we are going to solve this differential equation. And if you recall, we had those steps of separate the variables and integrate and use the initial condition, all that stuff. Remember that from like a couple days ago? If you don't, go to the last video. Okay. So if we want to solve this guy, we'll separate our variables. So I'm going to multiply both sides by dt, because that way I have dp equals 0.05 p times dt. I want p to hang out with dp, and so I'm going to divide both sides by p. So dp over p equals 0.05 dt. So there's our separate step. If you recall, the next step after separate is integrate. So we're going to integrate both sides. So on the left, we'll have natural log absolute value p. And then on the right, the thing that has a derivative of 0.05 would be 0.05 times t, because it's in terms of time on the right, and a plus c. Okay, so we did the integrate. Our next step is the solve for p. Usually it's solve for y, but in this case, solve for p. So if I do e to the on both sides, I'm going to switch pen colors here. So if I have e to the on both sides, remember e to the natural log of stuff is just the stuff. And then we have e to the 0.05 t plus c. Now, population's definitely a positive thing, but I'm going to go ahead and solve this algebraically following the same steps we followed in the past, partly just for that consistency, and also depending on context, you might have something that could be negative. Obviously not population, because you can't have negative people. I mean, you have negative people, but that's not what we're talking about. Okay, so p is plus or minus, and then I'm going to do that little switcheroo thing. So e to the c times e to the 0.05 t. And then I'm going to do that let c1 equals plus or minus e to the c. So if this is kind of fuzzy to you what I'm doing here, go see the last couple of videos. Okay, so that means our population is some constant times e to the 0.05 t. And then our next step is to use that initial condition. So our initial condition, you're like, oh, what? Going back to the original. Okay, population is now 1,000 people. Okay, let's call now times 0. So our initial condition is that now. I'm going to call that times 0, and then p is 1,000. So I have 1,000 equals c1 e to the 0.05 times 0. E to the 0, of course, is 1, so c1 is 1,000. And here's our equation, 1,000 times e to the 0.05 t, where t is time in years from, I'm just going to add quotes on that, now. So that is our first differential equations. And we will continue with another example that will be a little more complicated than this one. And I'm not saying this isn't complicated, it's just comparatively speaking. So stay tuned. Okay, we are continuing with our second example, and this is, if there was ever a fake real life problem, this is it. Okay, suppose you fill a tall, topless tin can with water. Of course it's topless, how would you fill it otherwise? And then punch a hole near the bottom with an ice pick, because this is something everybody does, clearly. The water leaks quickly at first, then more slowly as the depth of the water decreases. So if we have our can here and we fill it with water, and then we poke a hole in it, and then the water comes spurting out. Fancy drawing. Okay, so in engineering or physics, you will learn that the rate at which water leaks out is directly proportional to the square root of its depth. Suppose that at time t equals 0 minutes, the depth is 12 centimeters and dy dt is -3 centimeters per minute. So we're going to say that y is our height, in case you're wondering where this y is coming from. Okay, so write a differential equation that states that the instantaneous rate of change of y with respect to t is directly proportional to the square root of y. Let's unpack that question, or that sentence. So we have differential equation, so we know it's going to be that d something dt. Okay, instantaneous rate of change of y with respect to t. That is dy dt. So it's a very long way of saying dy dt. Okay, and then you know from lots of years of math that when you see the word is in math, it means equals. That was such a light bulb moment for me when I figured that one out. Okay, directly proportional to the square root of y. Okay, clearly I have a root y in there. When you see directly proportional to, you're not saying it, if this just said the rate of change is the square root of y, I would have that. But it's proportional to it, so it's just some proportion of it. So it's just like, you know, it could be 10% of it or whatever proportion. So we'll put a constant in here, and we don't know what this is yet, but we'll call it, I'm going to put a k in there. So then it says find the proportionality constant. That's the k. So this proportionality constant we're talking about is k. So we know that at time 0, the depth is 12, so y is 12, and dy dt is -3. So -3 is k times the square root of 12, so k is -3 over root 12. I know I could find the decimal for that or do something to clean it up. Some of y'all like to rationalize denominators, but I'm just going to leave it as that. Okay, so that's part A. Part B says to solve the differential equation to find y as a function of t and use the given information to find the particular solution. So when you see that, it means get rid of the plus c part, find the constant. You're going to get that using that initial condition thing. So that will be where we go next. So solving our differential equation, we will, of course, separate our variables. So I know I could plug the -3 over root 12 in, but it's faster to write the letter k than to write -3 over root 12. So I'm going to just leave it as the dy dt equals k times, and I'm going to write this as y to the 1/2 because I can't integrate roots, but I can integrate exponents. Okay, so getting my y's with my dy's and get the dt away from them, I'm going to multiply both sides by the dt. I'll divide by the root, or the y to the 1/2, so I have dy over y to the 1/2 equals k times dt. Remember that k is just a number. So we've done the separate, next comes the integrate. To integrate the left side though, I'm going to rewrite this as y to the -1/2 dy equals the integral of k dt. Now here's a spot that people mess up all the time. They see this dy over y to the 1/2, and then they crack out their natural logs, treating it like a dy over y instead of a dy over root y. Looking at that, is the numerator the derivative of the denominator? No, it's not. So this is not in that du over u form. If your exponent, if you have something that's like a dx over x to the something or dy over y to the something, if your exponent is anything but a 1 in that spot in the denominator, natural log does not come in. So be really careful with that. It's one of the biggest sources of error possible. I see it all the time. Okay, so we'll add 1 to the exponent, so I have 1/2. Divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2. And then, oh goodness me, I put a t in there that I should not have put in there. Pretend I didn't write that originally. Look at that, it's almost like it never happened. Okay, so integrating this, I had gotten ahead of myself. Integrating, we get k times t plus c. And then we want to solve for y, so we have y to the 1/2 equals kt plus c over 2. And then y equals kt plus c over 2 quantity squared. And you can do various things to clean this up. I'm not too fussed about it, to be honest. Okay. For the sake of not quite so many parentheses and such, though, I am going to, I'm going to come up here. I'm going to write this as a 1/4. So I have y equals 1/4 and then k, and I'll go ahead and throw my k in. So the -3 over root 12. Man, why couldn't the depth have been 9 or 16 or something? It would have been so much easier. Should have written it better. And then t plus c and squared. So that divide by 2 became the 4th because noticing it got squared. Be careful with that. Okay, so plugging in the fact that the depth is 12 at time 0, I get all of that. So really I have 48 equals c squared, because that's gone, squaring the c and then multiplying both sides by 4. So c is the square root of 48. So now I have y equals 1/4 times -3 over root 12t plus root 48 squared. So this is the solution to the differential equation. So that's part B. And looking at this, it's a quadratic. So answering the what kind of function is it? It's quadratic. Okay, plotting this as a function of t. I've already put this into my equation. I know it looks a little different, but so I have this in my y equals. I looked at the table to check some things. Namely, at time 0, is my depth 12? Yes, it is, so that's good. And then I threw some numbers in just to see what a good table would be, good window would be. So my window, I went 0 to 10. My y's, I went negative, that negative 4.1 was just sitting there, I left it. And my y max is 13. So here's my function. Now a reasonable domain would be going until it's empty, right? We can see that it's empty here, which happens at 8. You could solve that algebraically. You can solve it using your calculator, finding the minimum, for example, or use it finding the 0. Lots of options. So our domain then, for looking at plotting y as a function of time, for part C, would be, here's our graph, and then our domain would be 0 to 8, because it's not like the can is going to start refilling itself after 8 seconds. And how long does it take the can to drain? That would be 8 seconds as well. So that is our second example. So these differential equation questions, they show up as story problems most of the time, and the hardest part is the step 1 of translating the sentence into calculus. So look for those key phrases of like rate of change of blank, look for that. And then the phrases like, and the word is, that's a good one because it means an equal sign, directly proportional to, so watch those phrases. If it was inversely proportional to something, that would be like k over the number or the root y. So various things can happen. You just have to read it super carefully and think very, very carefully, and be careful with your algebra, be careful with your calculus. There are so many things that can go wrong with this stuff. Be careful with those integrations, be careful with all the things. So you're gonna go out and try to solve a few of these problems, and it will be a struggle. Be patient with yourself. You have to be patient. There's no getting around that one. And that should get you started on differential equations in context.